So since we are talking about the GPT-3 era, or we are trying to come or arrive into the GPT-3 era, we were introduced with the idea of in-context learning. So at the surface level, it looks very simple, right? So you give the model a prompt, and let's say the model, you're trying to give the model a prompt. For example, translate English to French, right? So you're giving it a couple of examples. Let's say you're saying that cat will translate into chat and dog will translate into chin, and what is house, right? So and then it produces something like maison. So basically you give it two examples, and the third example you left as a question mark, right? So completed the third example. So we call this idea as few shot learning. Why few shot learning? Because you produced few examples in the prompt for the language model, right? So, but what exactly is happening here? The model's weights are not changing in this few shot learning. Whenever we talk about learning, we always have this notion of, parameter based learning, where we are updating the parameters. Here we are not changing the parameters. The model is just computing the forward pass. The model is never computing the backward pass. Why? Because we're standing at the inference time, right? In the training time, the model will do forward pass, loss computation, backward pass, forward pass, loss computation, backward pass. But during the forward pass or during the inference time, it's only going to do or call the dot predict function or dot forward function, right? Where it's going to do the y is equal to mx plus c. Obviously, it's not going to be y is equal to mx plus c. It's going to be more and more nuanced. But you understand the gist, right? It's only going to compute the forward pass. It's not going to learn. We call this in a few shot learning because we are instructing the model with a few examples. Now, when we instruct the model with a few examples, what's happening is there is no gradient descent, there is no backpropagation, there is no optimizer, there is no Adams optimizer, no training loop, nothing. But the behavior of the model is still changing based on the examples in the prompt. So where is the learning happening, right? So that's why we call this idea as in-context learning or implicit conditioning. So a language model is fundamentally nothing but a conditional probability equation where it is trying to produce the next token given the past token, right? So what is happening is now, what is the probability of token T given the context, right? Let's look at it with this paradigm. What is the probability of token T pipe operator or given the context, right? So whenever we are including these instructions or examples in the prompt, we are not updating all the parameters. What we are essentially doing, we are just altering the current context. That's it. So the prompt is becoming the part of the model's input size. It's going through the model. It is helping us compute the forward pass, right? So we're nudging the model to compute an internal representation in this representation space, in the forward pass space, and we are giving it a few examples to produce this representation. Now, the model is not producing representation during parameter computation part, during the parameter update part. It is computing the representation during its activation phase, during its forward pass, right? That's why we say that there are no weight updates, right? So this was a little shocking part when this few shot learning observed, or when the performance was observed with respect to few shot learning, we were able to observe that without even learning, only by fine tuning the prompt, only by bettering the prompt and giving it more and more context and with more and more examples. So few shot means, you give some deterministic amount of examples. It was not like you give unlimited amount of examples, maybe 3 to 10 examples, right? One shot means you only give one example, zero shot means you give no examples, right? So that's how you should remember it. Zero shot, zero examples, one shot, one example, few shot, few examples, let's say 3 to 10 examples, right? Everything that you're giving is part of the weights, right? That's why there is no updation of parameters. That's why parameters are completely agnostic. We don't care, right? And the larger the model, larger and heavier the model, like GPT-3, better is the performance, even within context learning, right? So this means that the model might have already internalized the space of all the possible tasks during the pre-training. The prompt is selecting a behavior from that space rather than creating a new one, right? So what we really mean is that the model on an abstract level has already learned French, right? Or has internalized a framework of mapping English to French internally, right, during its pre-training. Now we are just triggering that behavior in the forward pass. That's it. So that's why the in context learning is not really learning, right? It's a way to look at things. It's a paradigm to look at the forward pass, and it's a way to reason why there are better performance results with giving a few examples in the prompt, right? So the in context window, or the context window during the in context learning, was acting as a working memory for the model, right? That's why the forward pass was able to produce a better representation during your inference stage. So we kind of know that in context learning is not something like a deeper idea of machine learning or a different idea like like reinforcement learning, right? So if machine learning simply said that a task is specified by a data set, a loss function, and gradient descent, in context learning simply says that the task or my task is rather specified by the pattern in the prompt. If your demonstration in the prompt shows a chain of thought reasoning, I will help the model simulate chain of thought reasoning. If your demonstration in the prompt show MCQ based reasoning, I will help the model behave in a way that it simulates the MCQ style of reasoning or MCQ styles of simulation, right? So this is what in context learning was. Now if we go one level deeper and discuss it with respect to the Bayesian idea, the Bayesian interpretation. So from a Bayesian perspective, the pre-trained model encodes a prior over a language, over the whole language patterns, right? And it has seen a lot of translation examples, classification formats, question answers pairs, MCQ pairs, chain of thoughts, right? Already in the whole language. That's how it has built a prior. Now, when you provide examples in the prompt, you are giving evidence, right? So the model updates its beliefs not by changing the weights, but by observing the kind of conditions that you have mentioned in the prompt, right? So formally, we said that what is the probability of token T given context? With Bayesian interpretation, we can say that what is the probability of output given the input and demonstrations, right? So the demonstrations are narrowing the hypothesis space for possible tasks, right? So so from all the larger prior space, the demonstrations helps the model just narrow down the search space or narrow down the space of producing that output. So given several translation pairs from English to French, the posterior probability of the model shifts towards translation task, right? Given a lot of arithmetic examples or a few arithmetic examples in the prompt, the model's posterior probability mass shifts towards that, this is arithmetic, I have to do arithmetic operations. This is why, we have a way of looking at it, and we call this notion or this paradigm as in context learning, right? Now, why were we correlating or why were we pitching this idea of in context learning over the idea of fine tuning? So when we were discussing in the last video that BERT produces a large model, a large brain model, let's say, or a large base model over, which has produced a contextual representation over raw text. Now we fine tune it to produce or to do domain specific tasks, right? This was the idea that we discussed in the last video. Now, why did we supersede this in context learning idea with that? Because we're trying to say that in the GPT family models, especially when there is a lot of scale of parameters, adaptation or learning happens through pattern recognition in the prompt also, right? So you don't always need to fine tune for every use case. The and you don't need to always have to undergo something like gradient descent or backpropagation, right? The prompt can help you achieve your particular task if you provide few demonstrations or few examples, which is nothing but few short learners. That's why the GPT-3 paper produced something which was called as language models are few short learners, right? So why this becomes a bridge to GPT-3? Because before GPT-3, we thought that generalization required supervised fine tuning, and we have to fine tune for all the domain specific use cases for generalization, and we need to have labeled data sets always for every particular useful task, right? But in context learning simply suggested that if your model is large enough, if it has learned the overall representation of the world of the internet over raw text, it has its prior ready over the language, you can trigger its posterior or you can better its posterior probability by providing a few short examples in the prompt itself, right? So this is what GPT-3 paper demonstrated, and this is, a GPT-3 paper did not demonstrate this by just a hypothesis. They produced series of examples, right, as evidence on how the performance got better with scaling the model and with the idea of a few short learner, or with the idea of providing a few short examples and zero short examples. So it compared against a lot of data and against a lot of domain specific tasks. So in the next video, we are going to discuss that paper in detail, and now these two videos have set the context for that paper, and the next video would be a natural extension to understanding what GPT-3 introduced. Thank you. I'll see you in the next video.